Hello, we're going to start with a lecture on chapter 1, which is just about um, measuring, doing experiments, the scientific method. So kind of just a background. These lectures are meant to either replace reading the text or supplement reading the text. So you could either read the text, watch the videos, or you could do both. Or if a concept is challenging when you read, you could just watch that section. So these are just hopefully to help you. So I'm going to share a PowerPoint, I think. Okay, so like I said, so chemistry, which is what this class is about, and it's pretty much an overview of a lot of topics in chemistry. Chemistry is a branch of science, so we're going to focus in this chapter really on experiments, doing science, how well do you know numbers, things like that. So we'll start out with a little discussion of the scientific method, which I'm sure you've been introduced to in whatever science courses you took in high school. So this slide just makes it clear that the scientific method is used in a lot of chemistry industry, chemical industry. So in the pharmaceutical industry, it's talking about how when you compared insulin profiles in the blood to a natural insulin release, or if you injected insulin, in each case you got an early spike, which means you had the potential for having low blood sugar later. And so they came up with this thing called Humalog. It's designed to mimic the body's natural release profile. So it made the insulin available at the right time. So the scientific method was used to design that drug. Okay, so the scientific method, which you'll use a lot in lab this block, and if you continue with any science class, starts out with making observations. So you'll always be asked to make observations when you're doing your lab work. Those will be both looking at things, were there color changes, were there solids formed, things like that, or oftentimes how much did something weigh, so a qualitative observation or a quantitative, which might include a mass or length, all sorts of different quantitative data. You're going to make an hypothesis. So you're going to try to explain those observations. So you might say, I made these measurements, and from my observations, I think that when you react copper with sulfate, you get a green crystal. And then you'll go on from there to see whether or not that's what's going on. So after you create your hypothesis, you design experiments, and you'll change one variable at a time in order to hone in on whether or not your hypothesis is correct. So if you think it's copper reacting with sulfate, you'll change the composition of your solution and have only copper metal in there. So things like that. So making sure that you can rule things out by only changing one thing at a time and not changing a whole bunch of variables. So in that process of your experimentation, then you'll test your hypothesis, decide whether or not what you proposed was a reasonable hypothesis. And from that, you might come up with a theory which explains the experiment or predicts what might happen in another experiment. So in order to test your hypothesis, you're going to have to do experimentation and often measurement. So this is just a slide telling you about the fundamental units that you'll use. So mass, length, temperature, amount of a substance, time, electric current, and luminous intensity. These all have units that if you use SI units, the standard unit system, then everything will be consistent. So if mass is in kilograms, if length is in meters, temperature in Kelvin. So it gives you both the name and then also the abbreviation for that type of unit. So all other units are derived from these fundamental units. So you might have length in meters, But if you have a three-dimensional object, you might have length times length times length, and that ends up being volume. So you could have your volume in meters cubed. This is a table I'd always give you on the test. You may or may not remember the prefixes, but if you have, for example, let's see, if you have a centimeter, centi in red right in the middle, and it's abbreviated to C, for example, and maybe you're talking about length, then 1 centimeter equals 0.01 meters. So this would give you the conversion of adding a prefix to a length or a mass and deciding how much you have. So when you measure mass, it's defined as the amount of matter in an object, and it measures the force with which gravity pulls on an object. And so these are two types of balances you might use in a Gen Chem lab. The one on the right isn't as accurate. We'll talk about accuracy and precision in a minute. And the one on the left is called an analytical balance. So you can really know the mass of an object more accurately. You can know it to 4 digits past the decimal place in grams. So a meter, this just gives you some idea. 1790, 1/10 millionth of the distance from the equator to the North Pole along a meridian running through Paris, France. Kind of random, but just starts you thinking about what a meter is. Each of these you can look at. The last one, 1983, the distance light travels in a vacuum in 1/299,792,458 of a second. So light's going pretty fast if you think about that small amount of time. So these are just 3 examples of the relative meaning of a meter. You'll also measure temperature, and you're probably familiar with all 3 of these. Fahrenheit is pretty common for reporting weather. So water freezes at 32 degrees Fahrenheit. It also freezes at 0 degrees Celsius or at 273 Kelvin. So this just shows you the relative temperature scales, and we'll be able to convert from one to another as we work through some problems. This gives you the equations that you'd use to convert. So for example, degrees Fahrenheit to compare to degrees Celsius in those first 2 equations. Not only is the size of the degree different, but it's also offset. So a degree Fahrenheit is 9/5 of a degree Celsius, and it's offset by 32 degrees. So each of those 2 equations going from Celsius to Fahrenheit or Fahrenheit to Celsius. And then the last one is the temperature scale, that's SI units, so we'll use it most often. And it's just has the same size degrees as degrees Celsius, but it's offset by 273.15. So Kelvin, you only have to add the 273.15 to degrees Celsius to come up with Kelvin. So these are some of the derived units I mentioned. So for an area, if you've measured something in meters, it would be meters on 2 different sides. So the area would be meters squared. Volume would be meters cubed because you have a meter on 3 sides. Density is mass per volume. So if we're working in SI units, it would be kilograms per meter cubed. Speed, distance per time. And in our SI units, it would be meters per second. Acceleration, meters per second squared. And you can look at the other ones. We'll use force, pressure, and energy as we get further along in our later chapters 8 and 9. Huh. Was that really in there twice? No. Huh. I don't know why it went backwards. Sorry. So when you think about a volume, it's important to think that you have 3 sides. I'm going to add this to what I convert here at the end. So we'll convert 1 meter cubed to how many centimeters cubed we have. I'll work through that. This is a pretty good visual that if you have a cube and it's a meter on all three sides, then you could think about how many decimeters cubed you have and how many centimeters cubed. So you can convert from different units of volume. And we'll look at that a little more. It really doesn't do it here like it should, where it shows you where the cubed comes from. So when you're measuring volume, there'll be lots of ways to measure volume. On the left, there's a graduated cylinder, which isn't a very accurate way. There's a volumetric flask, which is very accurate. Oftentimes, if you want small quantities, you'll use a syringe. If you look on the right, if you're doing a titration where you're trying to add an exact volume until you reach some endpoint, you often use something called a burette, which you'll use in this class. Density, as I said, in the lower right-hand corner is mass per volume. So it would be kilograms per meters cubed if we're in SI units. More commonly, you'll find it in tables like this table in the middle in grams per cubic centimeter. So this just gives you some idea of the relative value of density. So notice that a chunk of metal gold is a lot more mass in the same volume compared to something like water. Helium and air, much lower number of grams per cubic centimeter. So it just gives you an idea of the relative values. So in each of these, we're just thinking about if we're doing experiments, what kind of units might we use? So now this was density. So the concept of accuracy and precision will be important in your lab work. And so when we think about it, we're going to think about significant figures in measurement because that's part of knowing your accuracy and precision. So the accuracy is how close to the true value a measurement is. And precision is how well a number of independent measurements agree with each other. So when we look at this table, when we look at the bathroom scale, well, first let's think, we're weighing a tennis ball on a bathroom scale. And so they have this, oh, funny, I guess that makes sense. So 0.07 kilograms, if 1 kilogram is 1,000 grams, that would mean that this is that would be 70 kilograms is the value you get for the average of your 3 measurements. So a bathroom scale isn't giving you a number too close to the true number, and the numbers are very different from each other. In this case, you're getting an answer that's very close to the right answer, but there's variance in the numbers you measure. And the last one, it tells us here, has good accuracy because we're getting a number that's very close to the true mass. So the true mass is given up above 54.441778. And when we take an average of our 3 measurements, we're getting that number if we rounded the true mass. So that means it's good precision because each of the measurements is similar to the other measurements, and good accuracy because the average of those 3 numbers is very close to the true value. When you look at this one, it's very accurate. You take the average and you get what you would round 3 digits to, 54.4. But the 3 individual measurements are different from each other by up to 0.2, or 0.2 of a gram. So the precision is poor. You don't get the same measurement each time, but when you took the average, you got an answer close to the true number, so they're very accurate. And then this is both poor accuracy and poor precision. You get 70 grams, which is lousy accuracy when the true number is 54, and poor precision because you get anything from it weighs nothing in the second experiment to it weighs 0.1 kilogram. So when we're thinking about those numbers, we want to think about which of those numbers do we know. So significant figures is the number or the total number of digits recorded for a measurement. So when you go back in this example, like when you did it on the lab balance, you have 3 significant figures. And when you did it on the analytical balance, you have 6 significant figures. And when you do it on the bathroom scale, you have 1 significant figure. So generally the last number in a reported measurement is uncertain. So there's always some variance in that last number when you're measuring something either with a ruler or a volumetric flask or a mass on a balance. First thing you want to think about with significant figures is you can have exact numbers. So there are 7 days in a week, there might be 30 students in a class, and there aren't 7.1 days in the week or 30.2 students. These are exact numbers, and so you would say it's 7.00000 forever. So it has an infinite number of significant figures. And the 30 students also is 30.0000000. So it has an infinite number of significant figures. So when we count significant figures, zeros in the middle of a number are like any other digit. They're always significant. So we have 1, 2, 3, 4 significant figures in this number. Zeros at the beginning of number are not significant. So when you look at this number here, where did my cursor go? 0.00661. The 00 is only there to tell you that the 6 is in the thousandths place rather than somewhere else. So if you were to write it in scientific notation, you wouldn't need those zeros, and it would show you that you only have 1, 2, 3 significant digits, and the other two, well, 3 zeros are not significant. Zeros at the end of a number and after the decimal point are always significant. So if you look at 55.220, you wouldn't have to put that 0 there and it would still be 55.22. So if you put that 0 there, you're telling someone that I know that that's a 0. So that means this number would have 5 significant figures. Zeros at the end of a number and before the decimal point may or may not be significant. So when you say 34,200, you may not or you might know those 2 digits. So it would be better to write that in scientific notation, 3.42 times 10 to the 4th. So if you wanted it to not be significant, or 3.4200 times 10 to the 4th if they are significant digits, because they're also there to represent that you're in the tens of thousands rather than in the hundreds. So when you're keeping track of significant figures, these 2 slides you should go over 100 times before every test and always remind yourself to check sig figs. So if you're multiplying or dividing, the rule is that the answer that you get can't have more significant figures than any of the original numbers. So in this case, you're dividing a number with 3 sig figs by a number that has 4. Therefore, the answer has to be rounded to 3 sig figs because my answer can't have more significant figures than any of the original numbers. When you're adding and subtracting, it's a little different because you only know digits to the right of the decimal place if you knew them in both numbers you're adding. So when you look at adding 3.18 to 0.01315, you can really think that I only know 2 digits to the right of the decimal point in the first number. So it's really question marks after that. So if I add it to the next number, I'm adding a question mark to the digits further past than 2. And so you don't know those. So when you add the 2 numbers, you get 3.19315, but I don't know the 315 because there are question marks in my first number in those locations. So I'd have to round it to 2 decimal places, to 2 digits to the right of the decimal or 2 decimal places. So rules for rounding. So once you've done your calculation, deciding how many sig figs you have, let's say that you want to round this number to 3 sig figs. So if the first digit you remove is less than 5, round down by dropping it and all the following numbers. So if I want to round 5.664525 to 3 sig figs, the 4 is less than 5, so I'm going to drop that and everything else, and the number rounds to 5.66. If the first digit you remove is 6 or greater, round up by adding 1 to the digit to the left. So if I wanted to round that same number to 2 significant figures, 5.66, then The digit I'm going to drop, the 6, is bigger than 5, so I'm going to round the 5.6 up to 5.7. So if the first digit you remove is 5 and there are more non-zero digits following, round up. So that makes sense. I'm going to round up because this is greater than halfway. 525 is bigger than just 5, so I'm going to round it up, so it'll be 5.665. But if the digit you remove is a 5 with nothing following, round down. So if I want to round that number to 6 significant figures, my last digit I'm going to drop is a 5, but there's nothing after it, so I'm just going to round it down. I'm going to leave it as 5.66452. So we're going to do a lot of dimensional analysis in this class, which just means we may have had a balance that weighs in pounds, but we need grams in a calculation. So we're going to figure out conversion factors that will allow us to convert the units from one set of units to another. So this is just an example. If 1 meter equals 39.37 inches, then you could use either conversion factor. You could say 1 meter is 39.37 if you were trying to convert inches to meters, or if you're trying to convert meters to inches, you just flip that. Because what you're really saying, if you're saying a meter is equal to 39.37 inches, if you put one over the other, that's really equal to 1 because they're equal to each other. So we're going to create conversion factors and do a lot of dimensional analysis. So now if we want to use that conversion, so we're just going to use our first conversion, 69.5 inches, we want to convert it into meters. So we're going to multiply by 1 meter is 39.37 inches. Inches over inches, you can cancel units. That's like saying 5 over 5. Units are the same way. So the inches cancel, and in that process of multiplication, you've converted the inches to meters. Now I'm going to just quickly, in order to do this, you have to stop share. I want to show you just a couple of really quick problems. Okay. Okay, so the first one is just thinking about those significant figures in a calculation, because it's easy just to take two numbers, you're dividing them, the answer is going to have the same number of sig figs. Whoops, I did not share my screen, and that will create a big problem. Okay, so we're going to just look at this first calculation where you do several things in order to calculate x. So it's easy to think about what you do when you're just dealing with two numbers, but let's look at this. So it says calculate x and report the value to the correct number of significant figures. So first thing I did, because that's what I would do if I was calculating this, is do the subtraction. So when I did the subtraction, I get negative 122.887. And when you look at that, you'd say, oh, I'm probably oops, I forgot. Sorry, I changed that and added 2 zeros. That's why it looked funny. So now when I look at this, I might think, well, my numbers are all going to have 4 sig figs. Let's look at how many digits I should have kept on this. So when I subtracted this from this, how many sig figs should this have? I only can know it to 1 digit to the right of the decimal. So this will be 4 sig figs as well. So now when I look at this, I'll see that the answer will have 4 sig figs. And I rounded it. And I rounded it after I did the whole calculation, which is fine. You could also have rounded it here and then put this number in your calculator. I just kept my full numbers and rounded it, so you get a little different answer, but that's totally fine. Let's look at this one. just to make sure when you're thinking about a volume, it's not very bright. Oh, there we go. Okay, so if I have 1 meter cubed and I want to know how many centimeters cubed it is, you have to think that a volume, you've measured the length in 3 dimensions. So I'm going to have to multiply by 100 centimeters in 1 meter, but I'm going to have to do that 3 times. So it's the same as saying I have to multiply the length, which is in meters, and the width and the height by my conversion factor. And so you end up with, so one of these meters cancels one of these, cancels another one, or you can think of it as I did here, where once I cube this, I have centimeters cubed over meters cubed. So that means I had to cubed the 100. So you end up with 1 million centimeters cubed. So when you have the derived units, you have to pay close attention. It's an easy mistake to just multiply by 100 over 1 meter. So I think that is about it for chapter 1. Just an introduction to doing experiments, the scientific method, some of the units we're going to use. Sig figs and rounding numbers is super important. So even if you've watched this, I'd ask you to go maybe Xerox that page out of your book and take it with you everywhere when you're working on problems, so you constantly think about making sure you have the right number of sig figs. And dimensional analysis, so converting one unit to another like this, we'll do over and over and over. Each chapter will have several types of problems. So if this looks scary for you or you haven't done this for a while, you'll get used to it because we'll do it so much. So I will close out and come back with lecture 2 in a little bit.